Okay, I think we're live.
Right.
Um, so I guess we'll start in around 2 minutes. Um, yeah, I
Yeah, that
guess
will be cool.
yeah, we'll start in 2 minutes. Um, okay, I think we should start. We can start, yeah.
Yeah, let's.
Let's start. All right then.
Yeah,
Let me switch off the
I'll turn the video
camera.
feed off then.
Yeah, that.
Yeah.
Um, okay. So, okay, here are the questions. Okay, wow. A P6 Geo. The first thing I saw when I saw it, like, okay, a P6 Geo, I'm dead. Doesn't look that hard, but still, you never know. Um,
Wait, where is the algebra on the test?
hmm?
Where is the algebra on the test?
Hmm.
Five looks like some number theory or something,
Hmm.
probably. Or where's the algebra on the test?
I think these are algebra. I think this one should be algebra. It doesn't look very it doesn't look very number theoretic. Uh, let's actually try the questions. Let's do something like that.
Let's start with four.
Question
Let's
four
start with
then.
four.
Um, okay, so set of into n disjoint infinite arithmetic progressions. Okay, so they're infinite arithmetic progressions. Uh, they're disjoint. Common difference d1, dn. Prove that there exists exactly one index such that that is true.
Well, like let's say like give that term a name. Like let's say AI equals the product of all the DIs by uh,
All
uh,
right.
right. Did you move to the second page?
No. All
Okay.
right.
Did you?
Yeah, yeah, I've moved to the second page now.
Like let's give a name first. Like suppose AI equals the this term, right? And so we need to prove that exactly one. Uh, suppose the sequences are like SI contains AI,
Okay.
right?
Is it um is it
Yeah.
is it compulsory that all the di are equal? Um.
No.
No, it's
No.
not. Right, right, right. So you can have
No.
you can have something like 0, 8, 16.
Not zero.
Oh yeah, sorry. I mean,
D.
you,
Yeah.
oh, never. You can have something like 8, 16, 24, and so on, and you can have another sequence that goes 10, 12. Okay, I mean 10, 14, um, 18. Oh God, my goodness, my math is horrible. Um, 22, and so on. Straight. So the difference need not be equal, but
You always obviously have like by density summation of the reciprocals is one.
right, right. That has to be. Um,
This is by density. Say
hmm,
if you like expand this, then this gives you like summation of all the AIs is equal to product of all the DI.
right. Uh, okay. Can you just explain how you got that again? I'm not completely sure. This density thingy.
Okay, wait 1 second. So like I'm sure that like this can be proved by generating functions or something, but like the density thing is like you will define the natural density of any set S by basically this thing. Uh,
Okay, I've not seen this before.
so this is basically the density of S.
I think we should
Basically
try
what?
something simpler before doing all that.
No, no. This is like this just tells you what the relation. This relation. It's like quite elementary. Like something like if you have basically tells you what fraction of the first n positive numbers of positive integers for a very large n does the set cover. So for example, if you have something like a arithmetic progression like 2 2 plus 3, say like 2 plus 6 and like 8 and uh, then like 11 and so on, right? So you could say that on an like average, if you take a very large like sample space, right? So for a say suppose for a very large integer n, it is going to cover approx n by 3 of the natural number of the numbers in that range, right? So we can say like the density of this sequence is like 1 by 3.
Oh, okay, okay, that makes sense.
That's like a crude explanation of how sort of density works. It's like not very important for this. Probably the relation, this relation is probably going to be important though, because that's literally the only thing we know about the AI.
Hmm. I think right. Okay, so we have that's one relation we have. But I wait, give me a second. Right. Okay, go on. Let's see. So if we have the summation of the one by D inverses is one. I mean D inverses is one,
Yeah,
right? Okay, so they're asking us to show that that is true. Mm. So how do we so how, maybe we can try to find a specific character of that I it set the SI because I mean there needs to be something special of the SI for us to be able to get it out. Or is there
yeah,
something special about like, or maybe is there something like all those AI terms are in one thing, right? That could happen. All the AI terms are in one SI. So, like I mean, at the end of the day, I think we might be able to find something like characterize a SI somehow. Um,
characterize like each of the SI. So okay, so suppose like you write SI as uh, x d.
I think we should, try a few examples first. Um, like try to see if we can characterize the SI first. Can we let's just try a few examples. Um, so I'm going to page 4. Um,
Yeah, sure.
so say 1 9 uh 1 9 17 20 what 25 I think, yeah, 33, and let's say 2 5 um oh my god, no. Oh wait, what? 2 6. Okay, wait, I should erase this. I should learn math. um okay, what am I doing? What's happening? Okay, something's being wrong and I have no clue what that is.
Are you not being able to edit?
No, there's some sort of arrow. Go to page. Um, right. Let me try to erase it again. You know what? I'll just clear the page. Oh, this horrible.
Yeah, sure.
Okay, I'll just type it up actually. That seems easier.
Yeah, fair.
Yeah. So say 1 9 17 25. Um. Okay, wait. Somebody asked what density is. Okay, density is nothing. Density basically means what percentage of the uh yeah, a percentage of the numbers are covered by that sequence. So if you have, say, something of the form all odd numbers cover half of the terms. So density is 50%, I think. That's all. Um, I've never used it in a solution, and I really don't know. But this like seems like a nice problem. To be honest, I've never seen it. I'm not actually even seen it transfer into a useful condition into a problem. Like, I mean, I'm not that great, but still. So this is pretty nice. That we can actually make it a useful condition. It's not that complicated. I mean, it can be very complicated. I think there's some lots of study on that. Like, I mean,
Density.
that density is a very broad term, but here it's just a term that we use to regularize our thing and so on. So that's one. Okay, let's say two, 6, 10, so on. What else? What else can we take? 2, 6, 10. Maybe something like 3, 7, 11, and so on. How will we fit in a 4 here now? 4, right? So we can do 4 the old-fashioned way. Uh, or
Start with four, maybe.
hmm?
Maybe
4,
start with four.
yeah. Start with 4. I think I'll make I don't know, for the sake of it, I'll make a 20, 16 some difference, I think. And just to fill in the gaps, I'll make one. Okay. I'm creating a little too much convoluted examples, and but anyway, let me just so something like 16, no, not 16, 12, 28, so on. Um, got so many gaps. 5, I have to 14 and so on. Have I covered everything? Okay, 8,
Uh,
8 doesn't seem to be anywhere. So 8, um, 8, 17, so on. Okay, does this cover everything? Um, One, two, three, four, five.
I think examples for this problem would probably be like hard to list out or something.
No, I mean, w- okay, yeah, but let's just give it a try in any case. So what are the DI? DI, so I'll just write down a list of the DI. The DI are hit. Okay, I should have made something simpler. Um, so okay, wait, this is wrong. I think there should be 13, right? Right. So this is 16, this is 16, and 5 comma 13. This is 8, and this is okay. This is again wrong. It's 8 comma 16. You're right. So these are the DI, and okay. So what do we need to find? Okay. So what I was thinking was that maybe all the terms. Oh wait, is it possible that uh, the AI the AI are not even integers?
No, it's like a product of a lot of integers.
But is it possible that it's
In,
not an integer?
wait, like AI is defined as uh, like AI is if tuned to page 3, like AI is basically like product of a lot of integers, right?
But it's you're
It's
dividing an
defined.
integer, right?
No, the integer is already present. Like it's A3 is like
Oh wait, did I
one
read the
second.
question wrong?
A3 is like D1, D2, D4,
Ah,
D5 up till DN.
right. Never mind. It's just a product. Never mind. Right. I'm thinking what I'm thinking right now is that somehow
Hey, what if like two sets contain like the problem asks you to prove that exactly one. So I think we also need to prove that at most one contained first and then give a sort of a
what I'm
construction of
thinking
something.
is that maybe like they've given us a special product and like they're asking us to prove that the ith product exists only in the ith set, right? I'm
No, no,
thinking
no. Wait, no, that's not what they're asking us to prove. They ask us to prove that for exactly one index, the AI belongs to SI.
exactly, yeah, right. So for exactly one index AI belongs to SI. So I'm thinking maybe if it is true that you know for all indices I, all the AI belong to one specific SI. If it's
Oh, that is like
that
a
if that
very
might be
strong claim.
true, yeah, like I'm not sure if it's true, but it could be true. I mean, okay, this is a bad example, and it's definitely true here, because okay, this is a really bad example. All of them anyway, all of the AI anyway belong to this set. Uh, but is it true? Can you think of okay, is it in any case obvious by any chance that it is not true that all the
Uh,
AI belong to one set SI? Uh, okay, Milind asked, does density have something to do with the size of the sets? Yeah, basically, size is hard to talk about when the sets are infinite. So in some sense, this replaces that and tells us how often the numbers occur. So
so like for
hmm?
if you have something like a sequence that grows like very fast, like something say an exponential sequence, then it's like going to have like density zero because it misses like way too many numbers as you increase the sort of sample space.
But
Whereas if you have a
hmm,
very slow growing sequence like an AP, right, then it is likely to hit a like more fraction of numbers as you like increase sample space. So like as the example in like small example in like page 2 I put that's like if you consider the AP 2, 5, 8, 11, so and so on. So it has a common difference 3 and like you for a large set for a large n, it covers like somewhat n by 3 of the numbers in there. So in general, any AP with common difference d has density 1 by d.
In general, I
So
think it's a good intuition. I mean, I've never used it before, but now that you think about it, it might be good practice. I mean, it's a very specific scenario, but whenever you have some sort of sets covering the infinite plane, or you have some sort of sequences, you can talk about density. It might give out
not
something
really.
useful.
I mean, not really, but like for this specific problem, like density is very relevant because the summation of reciprocals equals one is kind of well known. I mean, basically, naturals have a density of a total density of one, and all the APs have a density of one by di for every ith AP, and so
No, I
summing
mean,
them should.
I'm just saying like it might be useful in a question with you know um like it might be useful looking into density. It might be useful looking into density and stuff like that. If anyway, let's
Depends, yeah, depends really. I think I've seen probably at most two or three other questions that actually use density apart from like in like actually a good way. I
hmm.
wouldn't say this problem actually requires density or stuff because the 1 by di equals to 1 can be proven by say generating functions or something. I think it's in PFTB as well.
I don't know if that is required to solve. I mean, I don't really see
No,
I'm
I'm
still
like, why for this problem you don't like require like
I mean, it
the
definitely does not require, right? I mean, they won't ask, like, they won't actually, you can't, they won't actually expect you to use something like density, but it might come out useful. It's like some sort of bashing or something. Like, there will be a solution with elementary means, but, you know, you
no,
might,
no, like I'm trying to say that
oh,
the main thing about like summation 1 by di equals 1, you can actually prove this by generating functions. Like, I mean, it's you can actually find the proof by GF by in like something like problems from the book. I don't recall the proof offhand right now.
hmm, okay. Okay, another thing I'm noticing is that all of these, okay, something is wrong with my pen. What's wrong with my pen?
Wait, so what you were saying is like if all the ages belong to one set, suppose Si,
Then we're
right?
done.
Then yes, okay. Uh,
Okay, that's working. Right. So how do we go along proving that?
Also note that di must divide ai, right?
Di must divide.
Can you go to page 3?
Right. Di must divide AI.
Di, like if you look here, right? Di divides the RHS,
Um.
like
Yeah.
if you look
Right.
here,
So
and
Di.
di divides all terms having a di term here, which is every like aj where j is not I.
Oh. This is a really nice way. Right. 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 So you're saying Di divides AI. Right. Huh. Oh, that's nice.
Basically, di must divide everyone, like every of the ages, because others have a I term in di term, and this guy is like from this relation. I'll just like write it up again. Yeah.
Okay. Okay. So what have you written here? I didn't follow.
Di divides ai.
No.
Yeah,
After
this thing,
this. No. Like, what is this SI you have defined?
like a general, like suppose like the ith set si is of the form this,
What's BI?
the first term of si.
BI is the first
I mean,
term.
like something like you start with 3, 3 plus 5, 8, 8 plus 5, 13, so on, so on. So bi is uh 3, and the common difference is like di, which is 5, right? So you are writing it as like 3 plus 0 into 5, 3 plus 1 into 5, so and so on. Just how you write an AP.
Okay. Okay, go on. Um,
So like if you have
oh, you just wrote S in that way, right? Okay, my mind is not in the right place. So if DI divides AI, um,
so you also know that D1, D2, up till Dn must belong to that SI, right?
uh, what? Which SI?
Like suppose if possible some SI contains all the AIs, right? Then you know that for every AI you can like set up an X such that AI plus, or let's say for every J you can set up an X such that AJ plus X into DI is equal to the product of all the DIs, because DI divides both sides, right?
Hmm.
So you must have that this term must belong to SI.
Mm, okay. Okay. I'm not 100% sure where you're going with this, but okay.
Yeah, I'm trying to figure out like if that is true, what does that imply?
Um, right. Is it true though? I
What?
mean,
No, I don't know. But seems like very uh, like too strong. Seems too strong to be true, sort of.
hmm. I mean, I want a counter example. That would be awesome. Let's. What do we do now?
Can we try to prove like this DI belongs to SI holds for like at most one index?
Hmm?
Uh, suppose can we prove that? Wait, I'll just add a note on the next page.
Which page?
The four, page four.
Oh wait. Yeah, I think this is not that complicated, right? Oh, we don't even need dense. Wait. Yeah. We anyway. We don't. Oh, give me a second. I think this is done already.
How?
So this go to page 3 and look at this sum you wrote, right? I mean, not
Yeah,
even that. Just sum all the
your
AI.
voice is breaking.
Um, okay. Is it audible now?
Yeah,
Right. So take the sum of this AI thing, right?
yes,
Take the sum of this AI and say if you collect one of those terms, if you collect say A1, right? Then
yeah,
all the others have D1 as a part of them, right? So
yeah.
so for instance, if the summation of AI is okay, this is done. We don't even need density or that summation thing, I think. We don't even need any of those things.
Why?
Just
What are
go
you
to
like trying to claim?
yeah, let me try to go to page 5.
Yeah.
Um, so let A equals sum of AI, right? And you can write this as say A1 um plus D1 D1 into something,
Have
because
you
D
like typed out something? I can't see anything on the
yeah, I've typed
page.
out something.
Okay, yeah. I
Right.
can.
So you can write this A as A1 plus D1 into something because D1 divides the rest of the terms.
Yes.
And you're done because if A belongs to this SI, okay, oops. If A belongs to SI, if A belongs to SI, then A1 also belongs to SI because it's A1 plus D1 into something. Like so if A belongs to S1, I mean if A belongs to
Right.
S1,
Like
oh yeah, in general, okay, in general, if A belongs to some SI, if A belongs to SJ, if A belongs to SJ, then you can write that
mhm.
you can write this as aj plus dj plus something. And if you subtract, I mean, because sj is basically stuff of the form something plus dj plus something. If you subtract a multiple of dj, aj will still be in that thing. So
Right.
you end
But
up with
like
aj as a part of sj, so you're done. And oh yeah, so this is a unique characteristic, and we
no. Wait. 1 second. How do you know that like the every suppose like for example suppose A was something like 1,000, right?
hmm?
Suppose, and say AJ was 400, uh, DJ was 10. How do you know that the partition is not something like, sorry, 1 second. Yeah, the partition is not something like 450, 460 up till 1000. I mean, how
450.
do you know that 400 is actually covered?
How do I know that
What you are
400?
basically suggesting is in the AP, if some
We know it
count
has
say
to be
X
covered. It
belongs to
has to
the
be
AP,
covered. I wait,
how
no, it doesn't have to be covered. That's true. That's true. Okay.
what you are basically suggesting is if suppose some X belongs to an any one of the APs, say SI, right? Then what you are suggesting is like X minus DI must also belong to SI, but that's not trivially true, right?
That's not
Might be
trivially
true,
true.
but trivially true.
Okay, that's you make sense. But wait, what was I
But that's
thinking? Great.
probably a
So
good start. Like that's probably, however, a good start to like what happens if like
no,
the
but
two of them
no,
actually.
listen.
Yeah, go on.
I think this still works because okay, say for contradiction that if that J is not a thing, right? J is not a,
J, come on.
suppose for contradiction that A, like where J, like A belongs to SJ, and suppose that AJ doesn't belong to SJ.
Right.
Uh,
Okay, go on.
now, AJ, okay, so now if you write A is equal to AJ plus DJ into something,
Yeah,
right? Um, AJ needs to belong to some set.
correct. Suppose AJ belongs to SK.
Okay, it belong.
Uh,
Say suppose AJ belongs to SK.
then
Mm, okay, my approach probably doesn't work. Yeah. Yeah. This probably doesn't hold. I mean, this just looks so useful. Uh,
wait,
I'm
can
not.
we just prove this? So is this probably true?
What?
Like the thing, like what you were suggesting is like, okay, suppose if X belongs to one of the APs, then X minus D as X minus D also belongs to that AP. Is that true?
Yeah, that's not true, right?
Wait.
Oh, it would have been nice if that was true, but
Can we prove it though? This is equivalent to saying that for every common difference, exactly one of its residue classes is like completely covered by the one of the APs.
so I think we can try and prove that. Try prove something like that at least. So take the example of 440 here. Can we try to make an example so that 440 is not a part of this set?
Yeah, I'm thinking. So you would write something like wait.
Yeah,
Suppose
okay, this
X
could
is
probably
equal
still
to,
work. Oh wait, you're in page 6? Yeah.
yeah. Suppose X is bi plus some y into di, but you have x minus di is equal to some bj plus zdj. Right. Then what does that imply?
Hmm, suppose, okay, you're going back to the old thing. Hmm, I mean, I think we should just try concretely first, like let try if 440 was not part of this, can you is it somehow possible to create another AP from this set, which is it's not right. I mean, I think it's
That's
somewhat
basically
obvious.
that's
Uh,
basically what I wrote.
right, right,
Like
right. I'm
how
just writing it more concretely. If D is the AP, is the
suppose you wrote
difference. Okay, suppose it's
440 as
yeah.
something like 435 plus 435 or something, and suppose yeah, but hmm, how do I like phrase this? Like suppose
No, no.
440 is in another sequence.
Hmm?
I'm trying to understand what problem does it create.
So suppose it has a common difference D, right? So if the common difference is a multiple or a factor of 10, which is basically the difference here and the AP of here, it will eventually contact to this, right? Because it will, if it's a factor of 10, then the AP which 440 is will eventually go to 450, and if it is a multiple of 10, it will go somewhere here nevertheless, right?
Wait 1 second. Right
On
hand
the other
side.
hand, if it does not have, if the and
I
even
think
even if it has a wait.
I got the proof for this.
Hmm?
So like assume like these two actually hold, right? Then on the first equation, suppose you are adding like r copies of di into dj, right? For some large integer r, right?
Hmm?
Then you can write the rh that the rhs must be a term of the si, right? Do you agree? Because it is of the form di plus y dash di, where y dash is greater than y.
Right.
Because like if some term say y belongs to a s, then y plus d must belong to an s, right? We are trying to prove that y minus d also belongs. That it's not the trivial thing. And for again here also again if you like add some large enough r di dj, right? Then this term again becomes bj plus some z dash di dj. Not just dj for now, right? So basically, this term belongs in both the sequences, right?
Hmm?
You get what I mean?
Right, right, right. I mean, yeah, it's basically saying that, if you have something co-prime to 10, if to co-prime to this 10, it will eventually meet. And if you are, and in this case, since the difference between these two is 10, if it's not co-prime as well, it will also eventually meet, which means that that's a contradiction, and this has to be in this sequence. And from here we
Okay.
can extrapolate
So,
backwards.
okay, 1 minute. So this proves that if x,
Okay, so we're done, right?
we
It,
did not prove uniqueness, I think.
Uniqueness? Oh no, uniqueness is. I think once we get that, you can get uniqueness from page 5, because uh, let's assume it's in some other thing, right? Let's assume A is in some SK as well. Then if you write AK,
Wait,
uh,
can you give me a minute? I'll just type up what I wrote in the previous page on page 7.
oh yeah, yeah. Um, uh,
Why is this problem so hard for a one? It's like so difficult to get your head around it. Uh,
hmm. Okay, what? How do we do uniqueness? Um, wait. Uh, Okay, look, A, no, A can only be an SJ. Okay, I'm stupid. What was I saying? A is uni since the SJ SI are disjoint, um, since the sets are disjoint, this means that
Right, I'll
A can
kind
only
of
be an SJ, and
performance
um, what does that mean?
in oh,
Yeah, thereby it's not that easy. I mean, okay, how do we prove uniqueness at this point? Hmm. Okay, let's see. Uniqueness. Oh, so we can say something like if okay, assume a contradiction. Okay, so let's say we assume a contradiction, and in this case, what happens is if say A is an SK. I mean, if this condition, if the problem statement holds true for some K as well, then you can write this as AK plus DK into something.
okay, let's move to page 7. I was like typing stuff off, so I was kind of
Yeah, I saw.
quite
Give me a second. Give me a second. I'm just trying something. Um,
on which page?
5. I'm writing over already written things. Uh,
Or just move to a new page, no?
oh, give me one thing. I'm just thinking. So if this holds for AK as well, so A is equal to you can write AK plus DK into something, and we're assuming contradiction. So we're assuming that AK belongs to SK as well. So then this whole thing. Oh yeah, the contradict uniqueness is really simple. It's a direct contradiction. Look here. Assume this. Assume this is assume contradiction and assume this holds for some other k as well. Then you can write a is equal to ak plus dk into something, right?
Yeah, yeah, I'm stupid. I get the point. Like it's
And if
basically the
yeah,
same thing.
and ak plus dk into something exists in sk, but we know
I
that
think
a only
basically,
exists in sj. Like it can only exist in.
basically these thing actually this actually proves, right?
Yeah, I mean it's
So
direct from
basically,
writing it in this form. Yeah.
what happened was something like if like uh, both Si and Sj have Ai and Aj, right? Then like you get that the product of all the Di's must belong to both of them, which is not possible.
And yeah, so we're done. Wait, we didn't even do use um
Yes.
density, right? We didn't use density at all.
Density gives you the like the relation in the first place.
Which relation?
1 by Di equals 1.
Yeah, but no, like what we didn't even use that relation.
Yeah, we did use it. We used it to like prove that Di divides Ai.
We didn't use that. No, we didn't use di divides ai,
Like, okay, like consider like when you like argue something like move to page 3, please.
right?
Suppose when you are arguing, like suppose product of all the Di is capital D. Suppose we are basically claiming that the set that contains capital D, suppose Si, must also contain Ai, right? So what is your argument here basically? Like if like D minus
Wait, I didn't
Di.
get you. Can you repeat?
Okay, move to page 3.
Yeah, I'm in page 3.
Yeah, so what we are claiming is basically if capital D belongs to Si, which it must for some I, then Ai must belong to Si, right?
Uh,
Yes,
Give me a second. If capital D,
capital D is the product of all the Di.
right?
So what we are basically doing is like we are basically using the fact that D capital D minus x times Di for all x must also belong to Si, for all integers x must belong to Si,
Hmm.
right? Hence, since AI is also zero mod di, it must belong to Si.
Right. So where did we use the density argument? Where did we use this 1 by d argument?
The di divides AI. You use this, right?
We didn't use it. We didn't use it.
Array, like okay, so like how do you get from d divides sorry d minus xdi belongs to Si to to AI belongs to Si?
Oh yeah, so we get that because we can write we can write di as um wait, give me a
That's
second.
yeah, go on. Go on.
Uh wait, why did we use this again? Why did we use capital D? I don't think we actually used capital D.
Uh, we did use it actually, like uh,
No, we
in
I think like according to me what the argument we made was let the summation of AI be capital A, right?
yeah.
Or say A, let the summation of A, go to page 5, let the summation of AI be A, and you can write A as AK plus DK into something.
I agree with you, but you get this identity from the density relation.
Which identity?
This A equals this.
No, no, no. A is A. We already know A is that. No, like that's the definition of A. A is the summation of AI. That's the definition of A.
Yes, and like how do you get it is equal to AJ plus DJ into something?
You write it. You write A1 plus D1, A1 plus A2 plus A3 till A n, right? And except AJ, all the other terms have a DN factor. No, like the way they're defined. Except AJ.
Can you explain me on a separate page,
Yeah,
like page 7?
page 7. So I'm saying that A is equal to A A1 plus A2 and so on, right? Till AN. And you can all like A2 is for instance the product of all the DI except D2. So if you take
How do you know
A2,
that?
huh?
How do you know that? How do you know that?
That's the definition of A2.
Okay, okay, go on, go on.
And if you take if you take A2 out and consider the rest of the AI, right? If you consider AI and consider the rest of the AI, they all have a D2 factor in them by definition. And so this A2 plus D2 into something. Like we don't need density at all.
I'm skeptical. Okay, go on, go on.
That's it, we're done. And after we use this argument you have written down in page 7, and we're done. That proves that the residue classes thing. And once we do that, then we're done because we assume contradiction to be, as a for uniqueness, and we're done. Yeah, we don't even need density or something like that. Then we don't even need that 1 by d argument. Nice. That's
Wait,
nice. Huh?
let me just like skim over what we did, right?
Yeah, yeah.
Uh,
Great. So I think question one is done. I'm somewhat confident question one. That's a good. I mean, it felt somewhat satisfying, so I think that's a nice solution. Um, so in the end, we didn't need the summation of 1 by d argument. Um,
so like our proof goes like we define A like this,
hmm.
right? Okay, so the first claim we make is like if x belongs to 1, then x minus d also belongs to it, right?
Right.
That's our first
So we
claim.
just need to prove that first. Yeah.
And the second claim we make is like if the sequence that contains A must also contain the corresponding AI, right?
Yeah, and then the third one we make is the uniqueness one, and we're done.
The third point is like the uniqueness. Okay.
Which we can
Give
prove
me
by
a second.
contradiction.
Give me 1 second for the uniqueness part. How do you? Okay.
We assume contradiction. Like in the end, if AK is if any AI is part of SI, that automatically implies that A is also part of SI. So that can only be true for one at most. And to prove that that is true for one at least, oh look, we didn't even try to prove our claim. Our initial direction was to try and prove that all the AI are in part of one SI, but we couldn't even we didn't prove that. That's probably not true.
Yeah, that's probably not true.
Yeah. Okay, so nice. Um, so we'll go to question two then.
Yeah, sure.
Okay, so let's
Actually,
read
give
this.
me 1 minute. I'll just like check the contradiction, the
Yeah, yeah, take your time.
uh, uniqueness part. Yeah,
Wait, did anybody on, YouTube find anything wrong with the solution? I mean, I'm not 100% convinced I think it's working. Uh, so,
yeah, this probably works. Yeah, let's move on.
question five. Right.
Yeah, yeah, this is the question.
Oh, Deba says the MOHS is less than 20. Yeah, I mean, it might be like 10 or 15.
15 probably.
Yeah, it's pretty hard for a one, I think. Um, I
Quite hard, yeah.
I think the key step is in the S minus D thing is just a detail in my opinion. Like it's something you notice anyway. I think the key step is trying to taking the summation of all the AI. Like if you take that term in the like the this term, the key step is considering to be honest, it's actually probably not that hard now that I think about it, because once you consider the summation of AI and try to analyze it, you're basically done because you can write it as something plus d into something, and everything else is details. So it's just finding that right sum, summing this over all I as well. uh, all right, so let's go to the next question. um, n and k be two infinite sequences. Okay, so there okay, I mean n and k are not infinite sequences. uh, oh wait, I don't think that's an NT. I don't think that's a number theory. I
Looks like combo now. Looks like combo now. I
lots of
said NT from the periodic thing, yeah.
it's definitely not number theory because we don't okay, it might be number we don't actually use any, it's quite combinatorial. You can call it algebra maybe.
Oh, which one? Problem 4 or 5?
4 4. Oh, I'm talking about 4. I mean
4 was
somebody
number
said
theory,
that
right?
at least for
It was
someone who's
obviously
bad,
number
Debai
theory.
said at least for somebody who's bad at NT, it's something you never want to expect. It's not that number theoretic, to be honest. We don't actually use anything. I think that we learn in I know typical number theory. It's very combinatorial for that matter of fact. We just consider the sum. It's quite algebraic. I mean, I suppose to be honest, that AGTC division is AGNC division is not exactly a clean one, right? I don't know. Maybe this might have been the number theory the
It
test.
was like quite number theoretic, though, in my opinion. Like,
Oh, really?
at least, yeah, I think like uh, the main, we could combinatorial thing, like if you're looking at it from the uh, some AI perspective, but like I think the claims and the proofs are mostly number theoretic, in my opinion. I think I think for me the uh, main claim is like you could think of the main part as like two parts, like the sum of the AIs and the second part, that is the X and X minus D thing. Second thing is like definitely number theoretic.
But in my opinion, that's just a like, detail. I think the main claim is, separating the. Okay, yeah, it's probably number theory, but it doesn't exactly feel number theoretic. Okay, yeah, let's go to problem five. Okay, so they're defining some equivalence between two sequences, and okay, they're defining something called equiperiod for a sequence. Okay, what is that? Okay, I have to figure out what this means. And okay, so what's the question? Suppose m infinite sequences with equiperiod k whose terms are in the range. Okay, the terms. So you have can be chosen so that no two chosen sequences are equivalent to each other. Determine the largest possible value of m in terms of n and k. Um, okay, the phrasing of the question looks weird. They're basically asking us to find the value of m, right? Oh, come on. They're just asking us to
Yeah.
find the. They're just. I mean, no. They're just asking us of equiperiod, different equiperiod sequences. Okay, they've just convoluted the.
Your voice is breaking. Mm.
Is it
Your
okay now?
voice is breaking. Yeah.
All right.
Okay, let me just read the question once. Like, I got confused. Okay.
Um. Go on. So, what are they saying?
Okay. So,
Right. So,
okay, one second. I'll move to
I
page
think I
8.
understood the question, but okay. It feels like there's a lot of trying to do. I'm going to page eight. Let's try a
Like,
small.
equivalent is like, you have like, I'll use, okay.
Let's try a
So
small
something like
example
if you have,
first. I think.
okay, I'll just write the definitions in any case if I forget. So,
Hmm.
RI equals R. This is the definition for equivalent, right? And K periodic is like, R of Ri equals Rj if and only if Ri plus K equals Rj plus K. This is like uh, K periodic.
Hmm. All right. I think we should try some small example. Let's try n equals 2, k equals 2, right? I think if they're asking us to find m in terms of n and k, they're they're mostly asking us to prove something like um, they're mostly asking okay, the solution shouldn't be too hard if it's a question five, but I mean by solution I mean the actual term. It should be something like n plus k or n into k or n power k or something like 2nk or something simple like
Yeah,
that. Um, uh, um, so yeah, so n equals 2 and k. So let's try to write down the sequences that can be true, right? Um, so let's say what can be true. So you can have 1, 2, and then what can come after that? You can have 1, 2, 1, 2, 2. You can go on like 1, 2, 1, 2. And I think this you have to continue after. You have to continue with 1, 2, 1, 2, 1, 2, right? What if you start with uh, a 2, 1? What if you start with a 2, 2, 1? And say you go 2 1. Oh, no, no, no. Okay, 2 1 2 1 2 1 and so on will be the same as 1 2 1 2, right? Oh yeah, so according to equivalence 2 1 2 1 2 1 and 1 2 1 2 1 2 are the same. So you can't have this. Oh, can you do a 2 1 and then you go 1? Is that possible? Um yeah, I think you can do this. So you can go something like 2 1 1 2 and then okay, so then you need to go 2 you need to go 2, right?
yeah.
Oh yeah, you need to go 2 and then you need to go 1 comma um 1 comma 1 and so on. Right. So this another different sequence. Um so wait, looking at this is I think anyway, so 1 1 1 1. Okay, so this is true. And so 2 2 2 will be the same, but I think we can select
Yeah,
this part of the sequence. But okay, what I mean is right, so 2 2 2 and so on. Right. So we have four so far. Uh, is anything else possible? Let's try. So if I start from 1 comma 2, if I start from 1 comma 2, then after that
is
we need
two
to go
one two
1 2
one the
1 2 or
same
2
thing?
1 2 1, huh? Oh no
Is
no no,
two
this,
one
oh
two?
sorry, I meant 2 2 1 1
Hey,
2 2 1 1, so on. Yeah, I think this is it. Because for each of these, so 1 2, you go 1 2 1 2 1 2, or you go 2 1, or you go 1 2 2 1. And then here you go 2 1 1 2 or 2 1 2 1. So that's going to be same as this. And after 1 1, you go either 1 1 1 1 or 1 1 2 2 1 1 2 2. And 1 1 2 2 1 1 2 2 is the same as 2 2 1 1 2 2 1 1. And finally 2 2. Yeah, I think we have exactly four sequences. So I'm leaning on something like n into k right now, maybe.
let's try the three case. Three into two. N equals three and k equals two.
Right. N equals 3, right? So let's try that.
Like
So
all ones is one, right?
okay, yeah.
You have like three very cheap sequences in one 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 and two 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 and so on so on.
These are all the same, so you don't need to write those. Oh, 1 2 1. Okay, so 1 2 2 3 1 2 2 3. Okay. Yeah, right. So that's a possibility. So starting from 1 1, you can go 2 3. Can you go something? Okay, you can also do something like 1 2 1 2.
Correct.
Let's do everything starting from 1 2 first. So 1 2 1 2 and so on. And what else can we do starting from 1 2? Can we go something like 1 2 3 2? Yeah, we can do 1 2 3 2, I think. 1 2 3
No, these
2.
are this and this is equivalent, right?
Is it? No, it's not equivalent.
Why not?
Because here the first and second terms are equal. Here the first, so here the second and third terms are equal, and here the second and fourth terms are equal.
I see. Like this is the problem, right? This,
They're not equivalent. Yeah.
right? Yeah. Okay. Not equivalent, right?
Um. So
I
okay.
think I ran out of waste.
Oh, you can go on top. I think fitting wherever it goes.
Okay.
Let
So
me just move these here. Give me a sec.
wait 1 second. Is these two sequences not like equivalent?
They are
No,
equivalent.
no. Okay. So
Which ones? Yeah, yeah. One one one
like
one and
all one, all one and all two.
all one and all two. Yeah, they're equivalent. They're all equivalent here.
Okay.
These two are not necessarily part of the thing. Um, Thank you, Donald Biden. Thank you. Uh, wait, okay, so I have a theory that if you choose for at least for this case, if you choose the third term, then everything else is determined already. Um,
I didn't get you.
oh wait, can you try something like 1 2 3 1? Is that possible?
Okay. One, two, three, one.
Um, Um, so is this a sequence? I just want to be sure. Is this a proper sequence?
Like proper as in like
What is it called? Is it
I mean
semi-periodic?
let's
What was the what is it called?
periodic. Yeah, it's
Equi-periodic.
obviously two periodic. Two it's two equiperiodic. Yes. But
Is
let
it?
me just like yeah, I mean obviously like this and this term is equal if and only if this and this term is equal. This call.
All right.
Okay, wait,
No, I
like
don't think
let
this is true. Look, this two and three are equal, but the one and one are not. I mean, the two and three are not equal, but the one and one are. Did you see what I was saying?
so no, I did not.
Oh, can you write the thing again?
Which can you repeat what to write?
The one, two, three, one sequence.
Okay, 1, 2, 3, 1.
No, I mean, this is not equiperiodic.
Why?
Look, yeah, sorry. Yeah. Oh, right. See, look, two and three are not equal, but one and one are equal.
Ah, damn. Okay, get it.
So this is not an equiperiodic sequence. Um.
Is it?
Okay.
Wait, one second. Does equiperiodic mean a bijection exists between the two? Not equiperiodic, equivalent.
No, wait. Let's try finishing these things first. Let's try. I don't think there are only four of them here. No, I think we can write more, right? We can write like something like one, one, two, two, one, one. Can you let's try writing all of these. What else can we write from this? Okay, we're doing a lot of case work, but I think it's important to see where this brings us. So hmm, oh, can we do something like one, one? Okay, so if one and one come, then the next two have to be equal. So it's either one, 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 or two, 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 two. And you can get all the cases of this. So you have two cases here. Wait, is this only five cases? So is it like n plus here or something? Or are there more cases somewhere?
I think there should be more.
Okay. Oh, is a one, two, one, three possible? One, two, one, three, and then we go one, two, one, three. Is this okay? Right? Oh no, this is not true either. One and one are equal, but two and three are not equal. Oh, come on. Um, so are there only
I
five
think
cases?
I think we should first like one second.
No, I just want to
Okay,
find
I'll just
everything here.
okay, give me a minute. If you have something like one two two one, 1, 2, 2, 1, this works. 1, 3, 3, 1
No, that
works.
this is the same as that one. 1331 is equiperiodic to this, but 1122 1122 works. Right, so the
Okay.
one. Um, 1122 works. So, okay, we got six cases. So maybe it's n into k. Uh,
This is a kind of a rigid problem. Like I think we should try to understand what equivalent sequence and
no, I mean,
aperiodic
I
sequence
think it
actually
would
mean.
greatly help us if we get our answer
I,
first.
I I agree, but like I think if we like kind of spend some time on characterizing them, I think answer extraction becomes easier as well. Like going to the examples
Let's
might
just
be
try this. Let's just find all the cases in this and we can maybe motivated by the thing. Like I think at this moment we should try some construction for n into k because I think there are only six. Are there only six? Um, let's try. Are there only six here? Oh, look, this sequence, the one, two, two, three is wrong, I think. This one, two, two, three is wrong because two and two are equal, but three and one are not equal. So this is wrong. So we're back to 5. So wait, I think we should find some way to use, the three numbers somehow because we're only using two numbers so far. Except in this 1, 2, 3 example. Um, so how do we use that? How do we use that example? Let's see. What sequence does exist? 1, 2, 3, 2. So are there like five? No, five looks like okay. Five is possible. Something like n plus k. Right?
Yeah.
Uh, so what are the cases? What's left? Okay. I mean, we can assume one comes first without loss of generality. Okay, let's try something systematic. So one comes first without loss of generality because you can always switch the terms. Then after this, either one comes or something else comes. Now, if one only comes, then the next two terms should also be equal. Now, if the next two terms are like two and two, right? Oh wait, can you do like 1, 1, 2, 2 and then something else? Like 3, 3, 1, 1, 2, 2, 3, 3. Is this okay? Um,
2233. This probably works as well.
and then again 1, 1. Yeah, yeah, this works. So 1, 1, 2, 2, 3, 3, then 1, 1, 2, 2, 3, 3 works. Oh wait, so it's not only repeating after four. You can repeat after six here. Um,
Wait, let's try equiperiod. Did we try equiperiod 1?
equiperiod one. Yeah, this 1, 1, 1 thingy. Oh no. No. Let's just finish this case and we can try the other case then. Uh,
Let's try the easiest case first. This like looks quite complicated. Like
I mean,
let's
we tried the
go
n
from the
equals
easiest.
2k equals 2 case. I mean, I just want to know
Uh,
how where this happens. Like what value? I think we should. Okay, let's do something systematic here. So if you do 1, 1, and then the next two must be equal, then it become 2, 2, and then the next two must also become equal, and you can do either 1, 1, in which case this it becomes the stop case or this case, and if you do all same, so you have this. So I think there'll be three cases for 1, 1 things. Okay, now let's do 1, 2. The other case is where you have the first two are different. Now, if the first two are different, then this next two must also be different. Now, if the next two are like there are what six cases for the next two, so let's try all of them. So, if the next two are like 1, 2, then it's 1, 1, 1, 2, 1, 2, 1, 2. If the next two are like 1, 3, then that's this. Oh no, 1, 3. Then is this possible? Oh wait. So if there is 1, 3, we can't do 1, 2 again after this. But what we can do is call this one. Wait, yeah, we can wait. Why did we can do 1, 2, 1, 3, 1, 2, 1, 3, right? Is this something wrong with this? Why did we not write this? Okay, right. So this is one case.
1 equals 1, but 2 is not 3.
No, the period is case, so not immediately the next one. Like you need to jump by
Huh?
two. Period is two, not one.
Yeah.
Yeah, so
Yeah. So 1
that
is
can be
equal
true.
to 1, but 2 is not equal to 3.
No, no, that doesn't matter. Like, that's not what they're saying. They're saying that if, say, 2 is not equal to 3, then 3 should not be equal to 2. Or in this case, if 1 equals 1, then 1 equals 1. Like, you should skip the loop by 2, not by 1, right? That's what the k equals 2 means.
Wait, what? Let me read the question once again.
So, yeah, this is sequence holds. So, 1, 2 holds, 1, 3 holds. Then, so then now how about 1, 2, 2, 1? Then this one holds. Then how about 1, 2, 2, 3?
Okay, this gives basically tells you that 1 equals 2 imply 1 equals 2 if and only if 1 equals 3. Okay, I get.
Yeah.
I get. Okay.
Okay, so let's do 1, 2. Oh, wait. So can we do 1, 2, 2, 3? Okay. Wait, it's here, right? But see, we can't do 1, 2, 2, 3, and then we can't put a 1, 2 here. We have to go with a 3.
Can we start from the beginning maybe for this place?
Oh yeah, sure.
I'm quite
Let's
confused on this.
let's go to the next page.
Let's move on the next page and like start from the beginning. What sequences we got for 3 comma 2?
Oh wait, I'll just write the sequence. Then since 2 and 2 are equal, then 3 and this have to be equal. Um, so 1, 2, 2, 3, and this goes 1. So yeah, we can do 1, 2, 2, 3, 3, 1, 1, 2, 2, 3, 3, 1. So that's another sequence. So how many sequences do we? Oh wait, we're nearly done. We just have to check the 1, 2, 3, 1 case. The 1, 2, 3, 1 case has, oh look, the 1, 2, 3, 2 case has been written, and we just need to make sure the 1, 2, 3, 1 case. Um, so what will come after this? So this can't be equal to this. So this case, this has to be either 2 or 3. Um, and since this is equal, oh, so should this be 2 or 3? Look, so this should be equal. This should be s- put 2 in between. So yeah, so since this should be 3, and so I don't want to keep, so this should be 2. And this also unique. Oh wow, 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 nice. So clearly if you start with 1, 2, we have all possible sequences. So we have what do we have? Not all possible sequences. So we have all possible cases, in which these two are different work. So how many cases do we have? That's one, 2, 3, 4, 5, 6, 7, and 7, 8, 9, right? So we have 6 plus 3, 9 sequences. Okay, so 9, so it's probably n par k then. Oh yeah, so that holds for this case also, right? 4 comes from 2 par 2. Uh, so the answer is probably n par k. And depending on this, I think I see a easy way to
Can you like
yeah.
list all the sequences? I got really confused.
Oh yeah, sure.
Can you list all the sequences?
So I'll just describe the sequences, right? So
It's just nine of the list. No.
yeah, sure. So yeah, I mean, so if we start from if we start from two of the same numbers, right? Like it doesn't matter what we're starting from, because you can always replace the numbers and they'll be equiperiodic, because you're just replacing the numbers, and
That's
like
right.
that.
Yeah.
So if you start from 1 comma 1, then note that because of the equiperiodic condition, um wait, yeah, so because of the equiperiodic condition, the next two need to be equal. Now, if the next two are equal, they can either be like, say, 2 or 3, or they can be 1. Two different cases. It's a different number or the same number. If it's the same number, you get, you can show that it's just 1, 1, 1, 1, 1. But if it's a different number, um, if you then say, without loss of generality, say it's 2. I mean, it doesn't matter if it's 3. You can just replace it and it'll still be it'll be an equivalent function. So now after 2 2, you can have, say, 3 3, and then go back to 1 1, and so on. Or you can um oh wait, what am I doing? Yeah, so, or you can, after 2 2, you can come back to 1 1, right? So the thing is, you have three choices if you start with the same two digits. Now, if you start with different digits, assume for the sake of like, you can always start with 1 2, or else it's just a matter of replacing the whole thing, so it's equivalent. Now after this, the next two, right? Now we have six choices for the next two digits. That is, because the next two digits can't be equal, or else it won't be equiperiodic. Since these two are different, the next two also have to be different. So we have six choices for the next two: 1 1 2, 1 3, 2 1, 2 3, 3 2, and 3 1, right? And as a matter of fact, as it happens, all six of them can work, right?
I see. I see. Yeah.
So the 1 2 1 2 case is 1 2 1 2, so on. um the 1 2 1 3 case is 1 2 1 3, then 1 2 1 3, and so on. Then the two one case is 1 2 2 1. Is this equiperiodic? No, 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 no. This is
Are
wrong.
you having some kind of echo?
Really? Oh yeah,
I
yeah,
can
yeah. I'm
hear
really
you.
sorry. Yeah, yeah, yeah. I'm sorry. Yeah. Oh, this is not the sequence. This is like this. 1 2 1 3. Yeah, I think this is correct, right? This is correct, right? I think this is correct. Um, 1 2 1 3. So one and one are equal. So one and one are equal. Now two and three are equal. Yeah, this is correct. Um, Now, yeah, this 1 2 1 2 1 1 2 2 1, where and the sequence is imported from the n equals 2 k equals 2 case. Uh, then the next thing is if you have 1 2 2 3, in which case you need to go something like 3 1 and then go again, and then again start. Um, so 1 2 2 3 3 1, keep going like this. This is just a shifted version of this one, to be honest.
Yeah,
And So, we did the 2 1 we did the 1 2 case, we did the 1 3 case, we did the 2 3 case, and now we're gonna do the. Oh wait, I skipped. Oh yeah, we did the 2 1 case as well. We did the 1 2 case, we did the 1 3 case, we did the 2 1 case, we did the 2 3 case. Now we need to do the 3 1 case and the 3 2 case, right?
yeah,
So, if you start with 1 2 3 1, then you go something like what do you do? 1 2 3 1. Uh, 1 2 3. Can you do this? Is this equiperiodic? Yeah, this equiperiodic. You just keep going 1 2 3 1 2 3 1 2 3, and in the last sequence is where the thing is 1 comma 2 comma 3 comma 2, and then you simply go 1 2 3 2 1 2 3 2 1 2 3 2 and so on. So so like as it happens for each of these cases, each of the six cases, you get again. This is really encouraging. For this you get three cases, and for this you get six cases. Um,
okay.
it's and uh, so in total you have in nine cases, and I think I conjecture from this that the answer should be of the form
This
n power
9 to
k.
the K is like, yeah, 9 to the K sounds good.
Yeah, n to the k, right? Um, it's only a conjecture, but let's we can try to prove this at this point. So now that we have tried, I'm somewhat confident that it's n to the power k. So as you said, I think we can try looking at the rigid structure. But although I think it's something really encouraging that we start, let's say n equals a general n, and n equals general n, and k equals some general k. We start with okay, okay, okay. Look, n to the power k. Okay, so look, that's what it signifies. N to the power k is the number of tuples, k tuples of range n, right? So basically, we're looking at the first, this 1 2 thing, the thing that we're starting with. So basically, for everything, so here in this case, there are like nine possibilities: 1 1 2 2 3 3 1 2 1. So there for 1 2 2 1 2 3, and for all the nine possibilities, it's saying that we have a unique sequence, right?
Okay, I get. Yeah, that's good.
So maybe we can find some sort of bijection between the set. Maybe we can find from any given unique say, like, show that from for any given, say, from 1 2 we can form a unique one. From 1 3 we can form, like, you can form a bijection between this and this, between the set of k tuples and between this the set of sequences. Then we're done. So maybe we can somehow try to find an algorithm. Okay, so bijections goes both ways, right? Like, I mean, the best way to prove bijection is to prove an injection in both directions, like in general. Uh, maybe we can try something like 1 2. I'm trying to find an algorithm. So what can we do? So like I here I started everything with 1 2. Here I started everything with 1 2, and here everything with 1 1. But maybe look, there are three sequences starting from 1 1, right? But this corresponds to the three numbers of the form 1 1 2 2 3 3. So maybe each of them can, if you apply some sort of algorithm, you can get something from each of these things.
Okay, I think like first we should like try to like understand what a equivalent sequence or a like two equivalent sequence actually mean. Like I think this problem is like very sort of rigid in the sense that you can like characterize both the like equivalent and keep equal periodic sequences like probably quite nicely. I think that actually helps. Now that we are done with the guessing part, I think we should focus on that first.
We can try that. I was just thinking that we can form some sort of algorithm. For instance, like something like start with any sequence and
Yeah,
choose
what I'm
yeah.
trying to
Yeah, we can
say
do
is
that.
like
We don't You can try you could like I think you made some progress on that direction.
yeah, like one direction is like obvious, one thing is like obvious, right? If you can like say biject one of the sequences to the other, then it's like what uh like then they're equivalent, right? If
Hmm.
like if suppose if a bijection between Si and Ti exists, then they're equivalent.
Correct.
And
So, exactly. To prove the bijection, like the best way is to, try to prove some, like going both ways. And I was thinking of some sort of algorithm that takes this AI into the thing. Takes the K tuple into the sequence. Something like, oh yeah, look at this. How about this? So choose the greatest number possible. Like, I don't think this works, but say like 1, 2, 3.
are you
Then
typing somewhere something?
Oh yeah, I'm in page 9 at this point.
Okay.
1, 2, 3. So if you have 1, 2, then choose the greatest number possible. So you have 3. Um, and from 3, after 3, what is the greatest? You can't choose 3, but you can choose 2, right? So this is a unique. Oh yeah, look, I think this works for at least one direction. So look, so you choose the greatest number possible. So like write down every starting choice possible, like 1 2 1 3 1 1 2 2 2 3 3, all the choices, and then for every free choice write down the greatest digit that you can write. So like after 1 2 you write 3, right? Now after, like, because 3 you have a free choice. Now after this you don't have a free choice because this has to be different. I mean, you don't have a complete free choice. This has to be different. The next digit has to be different because 1 2 are different, so 3 and something. So you can't write 3, but you can write 1 or 2. So write the greatest possible one, so that's 2. And then after this, okay, you don't have a choice at this point because um, the 2 and 3 are different, so this and this should be different. So it can be 1 or 3, but since 1 and 3 are different, 3 and something can't be different. So this has to be 1, and you get 3 here. We've already discovered the sequence, and this keeps on repeating: 1 2 3 2 1 3, and this keeps on going. So you have one sequence from 1 2 you get this sequence. Now if you start from something like 3 3, then you get 3 3 3 3. If you start from 1 2, then you get 1 1 3 3. After this you can't do 3 3. Oh nice, I think this works. um but how do you prove this? Uh, how do you prove this? How do you prove that you get unique sequences from any two of these? How do you prove that the equivalence is unique? So in all of them, uh okay, how do you prove this? Do you have any idea? This definitely, this algorithm definitely works. I mean, okay, not definitely, but I'm quite convinced it works. But how do you prove this? Uh,
Can you like give me another example? And
right. So,
which way are you going? Like you are going from a sequence to a tuple?
yeah, no, I'm going from a tuple to a sequence.
Okay, can you like explain on a new page, say 11?
Okay. So what I'm saying is, um,
Pick your tuple first.
okay, yeah. Oh wait, eeks. Wait, let me. Sticky pads are better, I think. Yeah. Yeah. So, okay, never mind. That is equally bad. Uh, Never mind. So let me tell you what I mean. So let's say you have 1, 2, right? And then you have another sequence 2, 3. Sorry, 1, 3. Oh wait, I forgot to type up 1, 1. Um, 2, 1, 2, 2, 3, 2, 3. And then you have three more starting with 3, 1. Uh, you know, uh, 3, 2, 3, 3, right? Um, so I'm saying that maybe choose the largest possible thing. So here you can choose anything for the next digit, right? You can choose anything at all. So choose the largest possible. So choose three. I mean, I think it works the same with the smallest possible as well. But yeah, so so here you choose three, and the next one you can't choose three because 1 and 2 are different, three and this are different, right? So you need to choose something for the next one.
I don't see anything at all written on page 11.
Your voice broke a little. Can you repeat?
I don't see anything written on page 11.
Really? I have written it on
Yeah,
page. Huh?
it just appeared. It just appeared, yes.
All right.
Can you okay, can you explain what you wrote
Right.
once
I
again?
just wrote all possible tuples first. All the nine possible n power k possible tuples.
Okay, next.
Next, I'm saying the way is do this algorithm. Choose the largest possible digit that you have freedom to choose. So, for example, in this case, the first case, you need to choose three because
Okay,
that's the largest possible. Now, after three, you can't choose three
yes,
again because that would violate the equiperiodic rule. So you can choose either one or two because 1 and 2 are different. So three and the next one cannot be has to be different as well, right?
yes.
So I say that choose 1 and 2, and so after three you can choose either one or two, but choose the largest possible. So choose two, and so do the same thing again and again. So after two you need to choose. It can't be three. It can't be two. After this, it can't be two because I mean both of them because of the equiperiodic rule. It can't be three. It can't be two. So it has to be one. And then you'll notice that it has to be three again, and it keeps going. You can determine a unique sequence. Do you see what I'm saying?
Okay,
And for the 1, 3 sequence, um, the next one can be three. After this, you choose two because you cannot choose three again. After this, you choose two. Now you have to choose two because 3 and 3 are the same, so now 2 and 2 have to be the same, and the next two also have to be the same, so you have to choose 1 and 1, right, and so on. And now this will become 1, 1, 3, 3, 2, 2, right? 2, 1, 2, 2 will become, for instance, 3, 3, 2, 2, 3, 3. You see what I'm saying? Each of these will have a unique sequence determined this way. Oh wait, but I'm not sure if this applies only to the k equals 2 case. Um, Let me just try something for.
okay. Let's actually try this problem for 5 minutes each, right?
Uh, Sure, I'll just be trying something here. You were
Okay.
saying that you had some ideas about the structure,
Uh,
so
Not really.
okay.
Uh,
Does anybody watching have any ideas? God, this paper is hard. If question three is this hard as well, no, something is wrong with them. Okay, something. I mean, they're MOPS, but still. Um, so let's try some k equals something. So k equals 3 for n equals 3. So maybe, so what's the sequence that will be formed from this? So I'll have to choose 3, and then I'll have to choose. Yeah, I'm somewhat convinced that this algorithm has to work. Uh, no, this cannot be 3. This has to be 2 because 1 and 2 are different. So 3 and this one have to be different. And naturally, 1 will come after this. So it'll come 1, 2, 3. I'm convinced that this algorithm has to work. But how do we prove this? Um, so what do we have to prove now? What do we have to prove? We have to prove that somehow this cannot repeat. So somehow, like two of these sequences are not. If we write down all these sequences, somehow two of these sequences are not equiperiodic. Somehow. Wait. In this thing, three is the. We can always write down whatever we want in the immediate next digit. So in this case, I'm always choosing the greatest digit. Nice. Because I'm choosing 3 as the third digit everywhere. And we can always do this. Like choose whatever you want as a third digit. Okay, so that's something to note while going the opposite direction. All right, so what is saying? So choose the greatest. Okay, I'm saying choose the greatest possible third integer, and choose the greatest possible third integer. And yeah, this question is sort of a bad question to stream because it's it has a lot of casework and trying, and it's not like the third question yesterday. There's much to explain. So it might get this question can get slightly boring when when trying to stream this question. But nevertheless, you cannot ignore the base work. It's not always very fancy. But anyway, so how can we prove that these two the increasing sequences are
I think I'm quite lost on this, to be really honest.
yeah? Give me 1 minute. I think I'm coming at something. Let's see. 1 1 3 3 2 2. So if say okay, let's assume for the sake of contradiction that two sequences are the same. Two of these sequences are the same. But then you will note that the third number in all of these is equal, right? Third number is equal. So if 3 appears anywhere else, the 3 must appear in the same slots. So 3 has to appear in the same slots, right? So so let's say something like A, comma B, comma 3, and so on. And 3 appears in one of these slots. So in the other sequence which you're considering, uh, C, comma D, comma 3, 3 must appear in the same slots it appears because we already have a point of reference for 3, right? If these two are equiperiodic. So 3, the positions of 3 are the same. Now, what can we do? Now, let's say a 1 appears here. Then the C, let's say 1 appears at some slot, some random slot over here. Then at the same slot down, it cannot be a 3 because
But that's fine, I
I
think.
think that's a small internet problem. Yeah, can you hear me now?
Wait, is it you or is it me?
I think it's me.
Yeah, yeah. Am I good?
Yeah, you're good. Yeah, so as I was saying, I
Okay.
think I got the
My
bijection here,
question.
like
Like,
on one side. So, the position of the threes and the two equiperiodic sequences have to be the same by the of course by for obvious reasons, because if two threes are here, then the two threes have to be equal in the same place. Now, if you take a one, then this has to be like one or two in this sequence, right? This has to be one or two in this sequence. Now, if it's one, then all the positions of the other ones will be equal, and the other ones have to be two. No, wait, does do the other? Yeah, the other ones have to be two. So the only thing that can happen to make this different? Aryan, can you hear me? Okay, am I audible, Aryan?
yeah, yeah,
Yeah.
yeah, yeah. You're audible. Go on.
Okay. Yeah. So
Go
what?
on.
As I was saying,
Hello.
hello. Yeah. Hello. Okay. There.
Yeah, go on. Go on. You're audible.
Right. So what I was
You are
saying,
explaining.
yeah, what I was saying is that all the ones have to be ones and the twos have to be two. So the only
Okay, your voice broke.
oh, I seem to be having a little bit of an interpret problem. Give me 1 second.
Yeah, sure.
Can you hear me now?
Yeah.
All right. So yeah. So now if these two are have to be equiperiodic, that means that the only thing that can make these sequences different is if the ones and the twos are exchanged, because we are fixing the position of the threes, right? If the
Correct.
ones and the correct. So uh, now, okay. So let's see why this sequence and this sequence are not equiperiodic. So 2, 1, 3. Now, if you exchange the 1 and 2 in one place, you need to exchange them in all places. But this is not happening. Now, look, it can happen here and here. But why will this not happen? Because the next sequence has to be 2, right?
Yeah.
Um, this has to be 3. Now, so what's happening here? What's happening?
Wait, you're writing. Where
Oh,
are you writing once again?
I'm writing in page 11. Hey, Rohan.
It isn't really visible.
Oh,
Where are you writing?
it's coming on the stream, I think. So,
One sec. I'll just like open Jamboard once again.
yeah, yeah, sure. We're doing question two. Um, I mean question five. Uh, I think we have this really I have this really we got this really interesting idea that like we tried a bunch of cases and we got the answer as n power k. Like at least that's what we think is the answer. I mean, we tried some a couple of hours. Uh, uh, no, I have this really interesting idea that we can find an algorithm, and the algorithm I'm proposing is that choose the sequences, right? Choose the like choose take all the tuples, and then at each step we at each step at the next step what we're adding is the greatest number we can add. Um, so here 3 is the greatest number we can add.
Can we
So we do it
maybe
because we
like
can add 1,
try
2, or 3
some?
here. Um, Here we can add 1,
Can
2.
we try
Huh?
something more along the lines of recursion or something? I'm not really a bijection. Like I'm not really very comfortable with bijection and stuff.
No, I think
I
we
think
solved
like
the problem. I like it. This is it.
we did. Oh,
Um,
to be
yeah.
really honest, like I'm pretty blind on the problem. Like, okay, yeah, go on.
Um, So what I'm trying, like, I think the general case should be an extension of this. So I think what we can say is that, choose a k tuple, choose any one tuple. Um, what we actually do is that we choose the greatest number that we can choose without, violating the conditions, and keep adding it to the next, and then we choose the greatest. So if we have a choice, we choose the greatest possible. And I am claiming that two sequences are, you know, um, um, different. I'm claiming that any two sequences will be different in this way, because the only way one of the sequences is same. Okay, I think I'm doing somewhat of a general case. Okay, no, I'm not doing something of a general case. So the only two ways, so we can always choose, for instance, after a n set, after a k tuple, we can choose n. We can choose n. Okay, I think this doesn't generalize very easily. Okay, God, there are a lot of details here. Yeah, what were you thinking about the recursion?
Maybe like try setting up a recursion or something. Like one thing is obvious, right? Like, okay, you are calling two sequences, say Si and Ti, to be like what? Yeah, equivalent if there is a bijection mapping Si to Ti,
Hmm?
right? And you call them k periodic if like you have a bijection mapping, suppose a bijection sigma mapping Si to Si plus k, right? So you can sort of think of this as like you are choosing the hi Rohan. Uh,
Hi, Rohan.
yeah,
I
you can sort of think this as like you're choosing the first like n guys, not n, sorry. Yeah, sorry, you're choosing the first k guys, right? And then like just going on with a permutation. Do you get what I mean to say?
Go on. I think I get it.
So, and there is like some for count. So suppose the number is like Sn comma k for, yeah. So like this is like trivially you can choose the tuples in n to the k ways and a permutation here in n factorial ways, right? So when does a permutation is bad? If the permutation is like has every character, then it's good, right? Like the main problem arises when like some members of the permutation is not like covered in here. Do you agree? Like sort of if you have something like the permutation you are selecting is like a 3 to 1 and the original sequence if you write is like 1 2, right? Then here you are supposed to write like then the corresponding sequence is like uh,
Hmm.
1 goes to the last, so there is no 1. Wait, what?
Uh,
Yeah, so
hmm.
this is yeah, so and then it's like 3 2 and so on. Wait, when are there an overcount?
Uh, l- hmm. I'm still trying to figure out what you're saying, but give me a. Yeah, go on.
Like what I'm saying is like you choose the first. Like, do you agree that it's k periodic if there is a permutation, say pi, such that pi of si is like si plus k, a permutation from like n to n.
Right, huh?
So what I'm trying to say is like you can think of a k periodic sequence as like you specify the first k elements and the permutation. That gives you a k periodic sequence, right?
Hmm.
In other words, like suppose you pick the tuple to be 1 to up till k, and the permutation to be suppose n minus 1, the reverse permutation, right? Do you
Right.
get what I mean?
Yeah, yeah, I
So
get what you're saying.
this gives you one tuple, not tuple. This gives you like yeah one sequence, right? So
Hmm.
but like trivially there should be n factorial into the k sequences, but now there should be more like overcount and stuff. How do you make up for that? I'm just thinking like which permutations and which tuples actually lead to an overcount or a
Okay.
bad or a bad not overcount like a bad sequence or not k periodic.
Mm, I'm still trying to figure out your approach. Give me a moment.
Yeah, sure.
Can either of you share the Jamboard and explain how you are approaching? I don't actually get it.
Yeah. If you I'll just explain the approach I was using, and then I guess again, and I guess Aryan can
Wait,
explain. Yeah.
I'll send you it. Send it to you. Which one is this 2 or 3? Abhay?
This is two. This is Jam 2.
Okay, 1 second.
Right. So, I in the meantime, I'll just, sort like
I
try to
think if
explain.
we can like try to like go to the next problem if we don't have any a lot of progress maybe in 10
Oh,
20 minutes.
yeah, we can do that. Um, I think that the ideas using can be generalized. Give me a second. Um, so if we are trying to generalize it,
Uh, who is anonymous? Wait, who is anonymous pumpkin?
RJ, I guess.
Right.
Let's see. Okay, so you know, just to get clear of mind, we can just step back and try to explain the progress of what we have tried so far. Um, so what I was trying was basically I was trying to prove a bijection between the tuples and the thing by creating an algorithm which I'm quite sure has to work, and the algorithm is as follows. So you take any a tuple, and then at each step you need to choose a number, right? So choose the greatest possible digit that you're free to choose. So for
Okay.
instance, you can always choose 3 at this step, but in the here you can't put 3 after this because that would violate the equi-periodic thing. So you need to choose 2 because you can choose either 1 or 2, and you choose the greatest possible. And I claim that this way you can make all the sequences this way. And it's this actually easy to prove for this case. That is for the k equals 2 case, whatever n is, for the k equals 2 case, this is quite easy to prove. Um, and I don't think this should be that hard in the general case as well. But I'm not sure how to prove this. I'm not sure how to prove this.
I'm not even sure what your algorithm is.
Oh yeah. So just to explain, my algorithm is that I start with the tuple, right? So here I basically start with the first two digits in all these cases. I choose with all possible tuples, Okay, right? And I make one sequence out of each of these. And so what I basically do is I choose the greatest possible number, right? So I can choose anything between 1 and n, and I choose the greatest possible one. And here, so first I choose 3 because 3 is the greatest thing I can do. And then I move on to the next step. Now in the next step, I cannot choose 3 because, 1, 2, 3, 3 will not be equiperiodic. So I choose the next greatest number that I can, which is 2. And
Okay.
then I move on to the next one, right? And here I cannot choose 2 or 3 or 2. So I have to choose one. And I go on and so on.
Okay, this is interesting.
Right? And at least this is easy to prove for the k equals 2 case that this thing works. Um, and the way you do that is that you notice that the third number, and in general for any k, the k plus 1 thing will always be n plus 1, n, right? The k plus 1th place will always be filled with n because you can always put n over there. So anyway, so you fill 3 and you notice that if, like, say, assume for the sake of contradiction that two of these are, equal, two of these are like equivalent. So that means that you'll notice that because 3 is in the same place in them, 3 is in the same place everywhere, like in the whole sequence. So now we only have to look at 1 and 2. And in general, for n equals something case, you have to look at everything but n. And so right, so and if say at any place, if say 1 and 1 are in the same place, then 1 and 1 have to be the same place everywhere else. Like by the equivalence, like by the definition of equivalence, if 1 and 1 are in the same slot somewhere, they need to be in the same slot everywhere else. Um, which will, which will cause 2 and 2 uh, remaining to be in the same place everywhere else, which will give the same sequence anyway. So the only thing you can do is reverse 2 and interchange 2 and 1 in this sequence. And that is not possible because I think you can indeed prove here in this case that actually not only is 3 fixed, like in the case if A and B are different, if the first two digits are different, then the next two digits are also always fixed, 3 and 2. They'll always be 3 and 2. And yeah, this is easy to prove. Oh yeah, and we my whole argument from that time is for this case at least is, is long and is not needed. 3 and 2 are fixed, so 3 and 2 everywhere else are fixed. So even 1 is fixed in the remaining gaps. So for this case, for k equals, and you can extend this by induction for, I think, for any n for k equals 2. Okay, this
Okay,
will
that kind of makes sense.
yeah, I'm just trying to prove this for the um general case, and I'm trying to think of something along the lines of um so calling two k tuples equivalent, if you can it's sort of the same pattern. Basically, if a equals ai, say the tuples are a and b, then if ai equals aj, then bi equals bj, then those are equivalent. And say for instance here 1 2 1 3 2 1 2 3 3 1 3 3, all these six are equivalent, and the other three are equivalent. um, I'm saying that for any given for a equivalent sequence, for an equivalent tuple, if we apply the algorithm, we will get the same. If you apply the algorithm for an equivalent tuple, I'm claiming that the next k digits also have to be the same, like for the equivalent tuples. And I think this is pretty obvious. Yeah, it should be true. Yeah, that shouldn't be hard to prove because it goes by the same pattern. So like for instance, if the in one of the sequences, if one of the tuples is something like 1 1 3 4 and the other one is like 4 4 1 2, then in the next one, say n equals 5, then you need to go something like 5 5 4 3, right? You need like it will have the same pattern of sorts. So the next part is same. And I'm also going to claim, okay, I know I'm being really not understandable right now, but I'm also going to claim that if two sequences need to be equivalent, it's compulsory that they're yeah, that's obvious. It's compulsory that they're the tuples that you got them from have to be equivalent. That's obvious because you know that part also has to satisfy that AI equals AJ then BI equals BJ rule. So that's there, and so this means that we're basic. Then are we done?
I'm not actually sure, yeah,
Uh,
but it sounds fine because, like, yeah, like the value you'll get is like n to the k, right?
yeah.
Yeah, that sounds correct.
I mean, like we tried lots of cases, and pretty sure n power k has to be correct. But the
Oh, you did casework. Okay, okay.
yeah, lots of it. Yeah. Uh,
Oh, I actually didn't do any casework.
wow. Okay, that's how did you guess the answer?
I didn't guess the answer even. Is the thing, right? I
Oh,
did.
you,
Damn, that's
oh,
like quite
I
smart.
no no. I just did. I got structure, and then I just counted it.
oh, nice. Mhm.
Yeah, but like I was getting n to the k, and I was like, wow, it can't be n to the k. That just sounds wrong. And for 1.5 hours, like even I had proof written, and I was like, wow, that just seems wrong, and it was correct.
You were able to solve the third question as well, right?
Yeah, that was like much before I finished this.
Oh, okay.
Let's actually try problem three. I have been like, my brain stopped working on this for a while now.
Okay, hopefully, yeah, yeah. Let's do that. I'll have a while to think about how to finish the solution. Anyway,
And actually, like, try writing this up. Actually, sounds like might give a better way to explain what you're trying to say.
yeah, I'll do that. Yeah, so let's try problem six at this moment because okay, if this is not easier than problem three, you know, if this typical problem six level, this test is too hard, so I'm assuming it's easy.
What is my? I was told by Rohan that this day is supposed to be easier than day one, but till now, I think both the problems were harder than corresponding one and two of like day one.
Yeah.
Wait, how? Wait, 5 is definitely easier than 2, and 4 is definitely easier than 1?
Hmm?
I think we spent 20 minutes on one, 45 minutes on four. Uh, I think I could actually solve P2 in some time. I could not understand nothing on problem five. I think that's my defense.
Yeah, we solved problem two much easier. Yeah.
What's your 4 ka proof then?
Oh, four. So we consider we got the proof that we got was yeah we consider the this term right call it AI right this one by D1 into product of this thing we call it the product basically it's a D1 into D1 the product till Dn and you divide it by so whatever we call it AI right we divide it by Di so we call it AI and we were like the question is asking us to prove AI is a part of SI. Um, so we consider. Wait, am I audible?
Yeah, you are audible. Go on.
Yeah,
Uh,
yeah, yeah.
uh, so so we consider the sum of all the AI. So A equals A1 plus A2 plus A3 till AN. And so let's say A is a part of some SK, right? Now we can write A as dk plus the sum of all the other d's. But now the all the other d's, sorry, all the other a's, right? We can write ak plus the sum of all the other a's. But all the other a's, by definition, have a d k in their product, right? They're the product of all the d's but their own. So you can take that dk common. So you can write a as a equals ak plus dk into something. For actually, you can do this for any k. But if a is a part of sk, then if a is a part of sk, that a you know, AK is also a part of SK. Like, did that make sense?
Yeah, yeah, got it.
Uh, right. So,
Yeah,
see,
okay. That's actually nice.
I mean, there are a couple of
Yeah,
details I think, yeah, but yeah, that yeah.
my argument was like by density, sum of 1 by di is 1, right?
Hmm?
Like one, call it density, call it whatever. 1 by sum of 1 by di is 1, right? So di divides like d1 d2 dn upon di divides this.
Hmm?
So if it is in like any term, then d1 d2 dn will also be there, and just the reverse argument. But yours
Oh,
is just
I
clean.
mean, like actually, Aryan wrote down the density thing, but it looks like that's actually not
We did
required.
not need it at the end.
Yeah. Hmm.
Oh, okay. Yeah. So
Okay.
yeah, I actually
Hmm.
posted day two. I actually posted. Day one, I didn't bother.
Hmm. Oh, okay. I'll check it out. I actually have to see. I think that okay. Never mind. Yeah. Yeah. That. Yeah. Hmm. Okay.
Okay,
Let's
so
let's
let's
actually do
move to
problem six.
problem
Yeah.
6.
We'll come back to five later, and I think I got the solution of five, but yeah, we'll come back to that later. Okay, this has to be easier. Um, so in triangle ABC, points D, E, F on BC, CA, AB, then uh, give me a moment. I'll just come back in a minute.
Yeah, sure. Okay, this like has a lot of circles uh, to begin with.
Yeah. Did Pranjal teach you any scam geometry techniques?
The Japanese stuff.
Yeah. Use
Uh,
Japanese stuff.
to be really honest, like I just know how it works. I've never used it on anything.
Yeah, I used it first time too here.
You're talking about the like uh, direction on a circle and then reduce or increase the radius, right?
Yeah, yeah, exactly.
Oh,
That sounds like quite eccentric. I have a feeling like this problem is like with a lot of circles, this might be a good like sort of a Monji problem. So how do you call it, Monge or Monji?
Monge, I think.
Okay,
I think
Monge
Monge
problem.
is French. I don't know. I mean, they
Okay,
don't pronounce any
can you
letters. I'm not sure. Huh?
move to page 12? Can
Yeah.
you move to page 12?
Oh, yep. I'm on page 12.
Suppose you have like in center of AEFD is like IA, right? And so on IB and IC. And suppose I is the in center of ABC and J is the in center of DEF.
Hmm.
Okay, so uh, what do we have?
Okay, so we are supposed to, okay. So they're asking us to prove that, um,
Uh, Disclaimer: I'm probably not going to do whatever Rohan is suggesting. I'll probably like just do normally.
wait, I actually wasn't there when Rohan suggested. What, I mean, Rohan, what exactly do you suggest?
Okay, so basically there's a sort
Oh,
of a geo transformation that helps. So suppose
oh,
you have something like you have a lot of I'll just explain in short. Suppose you have a lot of circles in the plane, right? So what you can do is like you can assume a direction for every circle, either clockwise or anti-clockwise, right? Such that if two circles are tangent, say externally, then at the point of tangency, their directions must be different, right? So this guy is going here, so this guy must go
So
here, right? Yeah.
Right?
Oh, sorry. And so next what we can do is like we can expand or we can reduce the radius of all the circles in the plane by any positive constant. So for example, suppose this guy has radius 10, this guy has radius 5, you can perform an operation to reduce the radius of the circles by, not reduce, say expand the radius of the circles by 5, right, plus 5. Suppose suppose clockwise is plus and anti-clockwise is negative.
Hmm?
So what happens is this circle becomes a 15 radius circle with same center. This circle becomes a point circle
Okay.
and do stuff with that. Yeah, that's basically a sort of a transformation. What and
okay,
Rohan was suggesting to use that, but I have never used that ever, so I don't know really how it
Okay, this is the
yeah.
first
works.
time. Yeah.
So
Yeah.
what? Yeah. So the basic idea is like if there are two centers at distance r1 plus r2, and if their circles are with radius r1 and r2, then tangency will be preserved in this transform, where
Yeah, yeah.
r1 and
Tangency preserve is probably the main point. Yeah.
and that's like the only property, pretty
Oh,
much.
right. Okay.
Yeah. Okay. The actual solution obviously does not use that. This I think only I did this.
Oh wow. Wait. Okay. So, oh right. So you prove that. So what you prove is that after reducing the things, you sort of prove that the radius of the you reduce the thing by the radius of the DEF, and then you prove that the new radius of DEF is basically the radius of the in radius, I think.
Yeah, but okay, I controlled how I'm changing stuff,
Right.
so it works
Okay,
well.
is the diagram like you can understand what I'm trying to do with the diagram?
Yeah, it
I'm
actually
probably
looks
not.
quite nice for a tablet drawn diagram.
Okay. Give me 1 minute more. I'll just add some more artistic changes. Okay. Let's. So suppose you're calling like the incircle of AEFT as omega A and omega B, omega C, right? And suppose the incircle of ABC is omega and the incircle of DEF is omega dash.
Okay.
Actually, let's rename J to I dash. Right.
Okay.
So if you like think about it, what does Monji on omega dash omega A give? I feel like this must have to do a lot with Monji because it has a lot of like tangent circles and stuff, circle tangents to line and stuff. So omega dash, okay. So
Uh,
omega and omega dash have an extremely center as A.
right.
Omega dash and omega.
D, one of those
Okay,
is D.
yeah. Omega and omega dash is a extremely center as D, and omega dash and omega A. Okay, what's left? Omega dash and omega A, right? No, 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 wait, I messed up one second.
Bye,
I'll just
Rohan.
write it. Okay, bye. Suppose you are applying it on omega, omega dash, and omega A, right? Then omega comma omega dash and omega dash comma omega A and omega A comma omega. This is A, this is D, and this is something fixed. Call it J for now. I renamed DFs in center to be I dash. So A, D, J are collinear, right?
Hmm. Okay. IJDA,
Similarly,
right? Okay, that looks okay. So,
similarly, BE JR collinear and CJF are collinear. So ADBECF conquer.
EAD,
BECF conquer.
right? Okay, wait. I need to look at the question again. I'm a little confused now. Oh, right.
Can we like select this diagram and maybe move it to the next page?
I'll have to try. Let me try.
Yeah.
Okay, give me a second. How do you select stuff? Okay, that's gonna be hard.
There's
Actually,
only a delete option apparently. Can't do it.
is there no select option?
Okay, so let it be. We can like just so 80 BCF conquered. That's a good
Okay,
start.
I did something horrible.
Yeah.
I cleared page 12. Wait. I think I can undo it, right? Yeah. Never mind. Yeah. Okay, never mind.
That had the diagram.
Yeah. No, it's back. It's back. Yeah. Yeah.
Can you undo it?
Yeah. I undid it. It should be back in a minute.
Right. Yeah, it is coming back. Yeah, it is back. Okay. That is a maybe a good start.
Um.
Let's just draw a simple diagram without any circle on the next page.
Let's see. What do we do here?
Sorry, this is I dash. Okay. Okay. Uh, there's a lot of sound coming from your side, I think.
Oh. Give me a moment. Okay. I'll mute myself for a little while.
Yeah, sure. So this is What if, damn, I cannot angle chase anymore. Think if I'm doing this correctly, this gives you IP DIC is what I'm basically doing is Abhay, are you there? Hello, Abhay, are you there?
Yeah, I'm here. I'm here. I
Okay,
I just
I'm
muted myself. Yeah,
basically do,
go on.
I'm basically like trying to figure out if the angles in here are nice, right? So
Okay. What do you think they might be?
yeah, I mean this is because of the angle bisector thing, all the angles are like nicely computable, right? Because angles of the form IBD, IC, etc.
Hmm. Uh,
I think this becomes, if I'm doing it correctly,
uh, wait.
yeah, this is one. Okay,
Hmm.
this is also this angle.
Wait. Like if we consider a triangle, right? Um, w- can if I like my geometry is not its freshest moment right now, but we could somehow draw another triangle, right? Like which has twice the thing, right? Which has twice the like whose circum whose in radius is twice the in radius of this one. Like we can somehow do that if I remember correctly.
Yeah.
Um, I think if you draw the perpendicular lines to that those in radius or something like that.
I'm not really sure what they're trying to suggest. Okay, yeah, one observation is like, uh, so DIB, DIBICI dash lie on a circle, right? So this is basically just angle chasing.
Okay, wow, nice.
Uh, okay, what's next? It's like,
They're given an intangent thing, right? Maybe we can use the condition that the sums of the opposite sides are equal.
the Python thing, right?
Yeah, the pit,
Python.
yeah, that thing, yeah. Maybe we can use that somehow.
Good point. Okay. Let me think for a while. Okay.
Hmm. So what do we do here? So, what ideas are you having right now? Say we draw, I can't hang
So
that
it's like
idea that that triangle.
BC and
Yeah,
EF, BC and EF are reflections about IVIC.
BCN.
BC and EF are reflections over IVIC.
Okay, that's a nice conjecture.
And that's quite obvious, right? Because of the angle conditions.
Wait, what? Oh, never mind, never mind. Right, right, right. Huh.
Alright. Uh, what does that tell you to do? What does that tell you to do?
Let's see, what do we do here? Okay, my mind somehow goes blank when it comes to geometry. Oh, give me a moment. I'll be back in like 10 seconds.
Sure. Okay.
Right, so. Mm, yeah, I can't like okay, like can you try to think of that thing? Like can't we like construct a
Can
triangle
you
over
elaborate?
another? Huh?
Yeah, I don't know how to do that.
No, I mean
Like,
like when is circumradius equals twice in radius? No, 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 no,
not
no, no.
circumradius.
Oh yeah, yeah, yeah. So when is so wait, 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 wait. So if we make this triangle,
Which
right?
one?
The one we have, right? If this
Okay. ABC or DEF.
DF,
Okay.
if we consider DEF, like if we construct another triangle such that DEF is the 9 point triangle, then it's okay.
Start.
Then will its in radius also be
What?
half?
Wait. What is the 9 point triangle?
Oh wait, wait, wait. What am I saying? Okay, never mind. Okay, I'm blabbering random things. Never mind.
Okay, suppose like the reflection of D in IBIC. Suppose that point is like
Wait.
uh, D dash. What can you say about D dash? Similarly, suppose okay, maybe it's time to look at two of these points at once.
Right.
Uh, so F dash and E dash.
Okay. This is turning out to be a hard problem to say the least. I think. Okay. Okay, I'm gonna try the problem 5 for a while. I think I should be able to do something about it. I'll be back in a second. I mean, I'll try this again in a second. Uh, because geometry just, lures a. I don't. I'm not able to think of geometry most of the time. Make progress.
Yeah, cool. Uh, I think geometry is like probably one of my strong points, maybe sort of.
Mm. These two series, four, five sequences are equal to these. Uh, I mean, I'm just I just had this idea that this geometry problem shouldn't be that hard because the previous two were hard. And I don't think it should be that hard, like, compared to a normal IMO 6. It should be easier than that. Uh,
No, I think Elmos are like the number six, the number 3 6 are generally
I
almost
mean, yeah, generally, no, I'm
similar.
saying that because, the first two problems are much harder than the usual. So this problem shouldn't.
Apparently, apparently people think 4 and 5 were easier than 1 and 2.
Oh,
What can I
come
say?
on. Oh, one. What do we do here now? Wait, this is getting treacherous. Okay, suppose for DEF, right? We construct a triangle going through that one side passes through D or the other side passes through F and the other side passes through E, such that the in radius is twice the in radius of DEF. I'm just trying to construct something so we can show the circle is equal, like something like that.
Yeah, go on.
No, I mean, can you define such a thing somehow? Like, can you define that triangle somehow?
Not really. I can't like think something regarding those lines.
Uh,
Yeah, let's move to the next page.
yeah.
Already know that AF is
Hmm.
okay, and okay, I can write it like this. How do you like deal with reflections over lines? I can't figure the relation.
Hmm.
I call got something else. Uh, can you move to page 14?
I am on 14.
Are you following what I wrote?
Yeah, I'm trying to figure out what it means. Yeah.
When I write I bracketed AEF, I mean circle of AEF. What I basically did was I backtracked the length case sort of.
Wait,
Right.
wait,
So
wait. Let me
this is
check what this means in diagram. AEF and DEF are tangent. You're saying that AEF and DEF, you're saying this,
this
the incircles are tangent.
in circles a tangent. The excess point, this is the same on 13.
Oh, nice. Is this true for all? Oh wait,
What is it?
is this like a general fact? I mean, in a pitot quadrilateral, if you divide by the diagonal, then the incircles will touch at the same point.
Yeah, probably.
Hmm, something to remember.
Okay, what's next?
Hmm. Bahula says, isn't trying this P6 without an accurate compass drawn diagram make it more difficult? It does make it more difficult, I suppose.
Yeah, yeah. So like that is a good point. So like I think a part of the problem is probably figuring out how to draw DEF given ABC, or how to draw uh ABC given, or how to draw DEF. Yeah, how to draw DEF given ABC, or how to draw ABC given DEF. I think that's also that. Yeah, that is a part of the problem. How to figure it out. Uh,
Hmm.
we are trying to do that at the moment.
Uh,
Can you like tell me how to like get ratios or something, or how to like understand D dash? I'm kind of interested.
how to
Like
understand? D dash.
D dash,
I mean, you could write D
like
dash. I mean, okay, this is probably stupid, but
D
you could,
dash,
yeah.
D dash is basically the deflection of D over IBIC.
Hmm.
Obviously, it lies on EF.
Hmm.
So
Wait,
how do you like trying to understand
D dash is the reflection or the projection?
reflection of D over IBIC? IBIC is. Can you move to 13? Page
I am
13.
in 13, yeah.
Okay, so this is IBIC. This line, right?
Yeah.
Did you see that?
Hmm.
And this is D, and this is the reflection of D over IBIC, and it lies on EF because EF and BC are reflections over IBIC.
Okay, nice. I mean, you can write, you know the ratios D dash F and D dash um, E, like that. I mean, like obviously that's equal to DF and DE. No, no, I mean DF dash and DFE. Uh, Other than that, I'm not very sure.
Can you come again? What you just said?
The lengths are equal, right? D dash F dash is equal to DF dash.
D dash F dash is equal to D. What? Can you what?
You
Did
told
not get
that
you.
D dash is the reflection of E dash F dash over
No,
D.
no, no. Okay, I'll just write it. D dash is D reflect over uh, IBIC.
Oh. Yeah, so you can write DIB is equal to D dash IB.
That does not really help.
I mean, yeah,
No, I'm
like the
trying
thing
to
is,
think.
maybe you can, like, that's the only length condition you can get. I
How
think.
do you like incorporate D dash with E and F.
Uh, I'm not very sure. Ooh, 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 what do we do? Oh, that's a nice song. Ooh, 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 what do we do? Okay, I'm a horrible singer, but yeah. Hmm. Okay. See, we take the perpendicular. Um. Oh, okay. Let's see what we do here. So does anybody have any ideas? Um. So what do we do here? Can we try a different approach maybe?
Different as in.
Try a different approach, I guess.
Yeah, I
Uh.
am like I want to kind of do this length chase sort of stuff with D dash, understand how that really works. Uh, uh,
Let's see. Hmm. Okay, so. Um.
There's a cloudy noise sort of coming from your feed.
Oh. Um. Give me a moment. I'll Try something. అమ్మా ప్లీజ్ కొంచెం వాల్యూమ్ హాల్లో కూర్చుంటావా ఏమో కొంచెం డిస్టర్బ్ అవుతుందంట డిస్టర్బెన్స్ okay hopefully it will get better now in a while um okay let me I think I got what to do in the fifth question give me a minute I'll just do that
Oh, you do cool.
let's see hmm. uh so if we assume two of these are equal and we can say that they're equal all the while okay I'm not really writing anything here but okay wait one one two three three hmm. Okay, we seriously need a new ideas. Hmm. Uh, right. Got anything?
Not really. I'm thinking.
So,
Don't sing lol.
okay, I know I'm bad at it. Okay, పద్ధతి నేను అప్పుడే చెప్తే టైం Six. Ajay, Ajay, I'm doing something live now. Please go, Ajay. No, I won't take it ever again. No. नीचे दो sound అవుతుంది డోర్ క్లోజ్ చేయొద్దు uh, Rohan, we're trying to get six. Um, we're not that
Can
making
you
that.
help us? I mean, I'm probably being very dumb. So, like, what we did was like, suppose it is kind of like we got some observations. The first one was like ADBECF conquer. Like the second one is something like uh, you have DIBIC and I dash lie on a circle. Next one is something like AEF and DEF. The incircles of those two triangles are tangent. Right. So next, what we do also another thing is like EF and BC are reflections about IBIC. Right. So what this motivated me is like you reflect D over IBIC to get D dash. I feel like you can sort of maybe length chase with D dash, but like I'm not really sure how to do it. That's what I'm basically trying to figure it out. I get the feeling it's possible, but well, I'm probably being very stupid. Can you figure out a way to like find lengths WRT D dash, like relating to D dash E, D dash F, etc.
Hmm, not very sure. I mean, you can go for trigonometry, but I don't see any other natural way to get lengths. Um, uh, okay, how much more time will you give? We're not really sure actually. How much time will we give? I think I got two. I mean, to be honest, I mean, I got the fifth problem. I mean, um,
10, 15 minutes maybe if you don't make any more progress.
yeah, Aryan, I think I got the fifth problem. It's the thing is that there are too many details to figure out.
I see, I see.
But like I'm confident that I got the question. I mean, I'm somewhat confident. I'll just have to type it up later and think. But okay, let's try the geometry again now. Uh, Okay, what can we do here? Like, I just want, I can't help think that we need to do something like that because every time some sort of computational thing is asked in like by computational I mean something like twice that I can't help but think that we need to prove equivalence to already known things like in the sense that if they ask us to prove that that angle is twice that angle, we construct some other angle which we know to be twice that angle and show that they are the same. So in this case, I think that we could somehow construct another circle and show that this one and this one are the same. Like you get what I'm saying?
Yeah,
Uh,
I'll spend 10 minutes more on this idea and then maybe go to something else.
right. Hmm, so, what do we do here now? Uh, so suppose we have a wait, no, that doesn't work. What do we do here? Okay, this is going a little slow. Okay. Oh, right. So I think I got problem five. Okay, I'm gonna have to seriously try problem six though. It's not exactly my wheelhouse. Prithoj, we didn't actually get it, so we can't actually speak so far. Um, we're not sure actually. Um, not sure if it's easier or harder. What do we do here? What do we do here? What do we do here? Hmm. Mm, okay. Uh, think
Yeah.
I
Yes.
um. Oh, wait, 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 wait. No, I mean, I'm going back to that thing I told you, right? I think it's one of those things. Can we, like, drawing the extra triangle such that the incircle is twice and comparing it? Uh, because I remember seeing something like that. The incircle is twice. I'm not sure where I saw it, but I did. Um, oops, sorry for the disturbance. Okay. How do we do this? Oh wait. Wait. Hey, listen. So we want an encircle. We want the encircle to be twice, right?
Yeah.
So we just need another triangle. Like suppose we are able to find another triangle which is exactly two times the size of this DF, right? And so we basically and it is of the exact same shape as well. So if it's the exact same shape and it is twice the size, then we get that the incircle will be twice for that triangle, and we can somehow compare it, is what I'm thinking. And we get that using the midpoint theorem, right? That the small triangle. Okay. So the EF need not be parallel. Okay, but we can construct a triangle that way. Are you getting what I'm saying? If we
No, no, I'm not understanding.
right. So let me concretely tell you what I'm saying. If we draw a line through D parallel to EF and draw a line through E parallel to FD and do the same thing, we get a triangle. Hmm? Can you just draw the thing
Yes.
in page some page? So okay, like like come back to page to come back to page 12.
Your your voice is breaking. Page
Uh,
12, okay. Yeah.
yeah, right. Um, right. Oh yeah. Can you hear me?
Yeah, can you come again? Your voice
Yeah.
broke
So
for a
so
moment.
yeah. So draw a line parallel to EF through D, right?
Okay.
Um,
Yeah.
you're in page 12, right?
Yeah.
Okay. Can you just draw that line, right? And do the other same thing for the other two sides,
Right.
right?
Oops. Sorry, just 1 second.
You let it be. It's okay.
I made a blunder with this. Yeah.
Now this new triangle will have encircled twice of DEF, right?
Yeah.
Huh?
Yeah.
So what if it has it will have it will have what encircle twice of DF. Now what if this has the same it looks like it could have the same encircle as the one of ABC.
And that is like too strong a claim, I think, really.
I mean, it looks possible. Okay, this would have been easily verifiable if we had a proper diagram. Um,
I have a hunch feeling. Is it possible for me to like share screen and you can present it?
uh, That would be a little hard. It would take some time. So,
Okay, can you like I'll instruct you and can you draw stuff on GeoGebra?
GeoGebra, I think it's gonna take time to draw all this. So yeah, okay, fine, we can do that.
Can you open GeoGebra once then?
Okay. Oh, we shouldn't be using GeoGebra, but
No, 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 okay. I think we'll end
yeah,
anyway soon. I think. Can you
yeah,
open? I have a hunch feeling regarding D dash E dash. I'll just check if that happens. Open
yeah,
GeoGebra. Yeah.
it's opened.
Okay. What you do is like you draw a triangle DEF,
Okay.
draw its X
Um,
touch point, draw the DX touch point on EF and call it D dash.
what? Oh, give me a second. Okay, I drew ABC.
Draw DEF.
Okay, wait,
No, draw DEF.
I'm gonna have to rename it.
Okay, what I'll do is like give me 5 minutes. I'll draw the diagram and I will send it to you and you can open that.
Mm,
Right. Uh, Wait, give me 2 minutes.
you know what? I think yeah, okay.
Okay. Uh,
Oh,
okay. My dash. I'm actually like drawing that. I have a hunch feeling regarding it, right? And I'm just verifying if it is possible to be true. Uh, yeah. Bye, people.
oh wait, wait. Guys, so yeah, I think we're not able to solve P6 right now. Uh, and it's getting really late, and I think we should end. So I'll type up I type up the solution we got for P5 and P4 and the other three as well as soon as possible. But we were not able to get P6, which is really unfortunate. I'm pretty sure some of this
Uh,
has to in this way, but
okay, then
so
bye,
guys,
guys.
bye. Thank you for coming, and
Yeah.
we couldn't solve P6. Bye.